Welcome to NASA STEM EPDC Quick Bits Big Ideas in Science content. NASA STEM Engagement and Educator Professional Development Collaborative provides NASA resources and STEM strategies for STEM engagement. In this series, we intend to reach educators, parents, and caregivers to quickly explain a specific big idea in STEM. We will introduce a NASA example of how this idea is applied in the real world, and finally, we will demonstrate step-by-step how to lead this activity at home or in the classroom with your students. You might invite your students to watch with you at that time. We invite you to join us as we learn more from our specialists. Let's get started.
Hello, my name is Barbie Buckner, and I am an education specialist at Goddard Space Flight Center in Greenbelt, Maryland. For today's big idea in science, we are highlighting bone density. In particular, we will highlight bone density within microgravity on board the International Space Station. Using cereal to represent that of human bones, students will identify the effects of decreased bone mass, investigate how force may affect bones of different densities, and describe why healthy ones are important in space and on Earth. Some bones have more cells, which means they have higher densities. Disuse or inactivity will lead to a decrease in bone density. Making exercise an integral part of the astronauts' daily routine aboard the International Space Station. Let's listen in as educator astronaut Joe Acaba stresses the importance of exercising in orbit and dives into the science behind what happens to bones and muscles in microgravity.
Hey there, my name is Joe Acaba, and I'm living and working on the International Space Station as part of Expedition 53. One of the best parts about living on the space station is being able to float. Just like you walk from place to place throughout your day, we float from place to place throughout our day. However, we have learned that the same thing that allows us to float, microgravity, is hard on our bodies over time. Our muscles and bones are made of millions of tiny units called cells, and these cells can have problems in microgravity. Up here on the station, bones and muscles no longer have to support the weight of our bodies, so they get weaker. Astronauts could develop something called muscle atrophy, where our muscles become weak from lack of use. Each bone in your body is made of cells too. A healthy bone has more density than an unhealthy bone. Weakened bones can lead to a disease called osteoporosis. Fortunately, our scientists at NASA have figured out one way to keep astronauts healthy and strong. It's called exercise. Let's take a look at how astronauts exercise in space. This machine here is the Advanced Resistive Exercise Device, or we call it ARED. It simulates free weight exercises in normal gravity to work all of the major muscle groups. ARED's primary goal is to maintain our muscle strength and mass so that we have less of a recovery period when we land back on Earth. All right, so there's looking at lifting. But what about a little cardio? We have a treadmill for that. Let's check it out. Staying physically active helps both astronauts in space and humans on the ground to stay healthy. And it prevents muscle atrophy and osteoporosis. Now you can try the activity connected to this video to learn more about muscle and bone cells. I'm Joe Acaba, and I hope you enjoyed learning about exercise on the International Space Station. We'll see you next time.
Wonderful. Now let's investigate bone loss and its effect in this activity. Items that you're going to need include Corn Puff cereal or other alternative, understanding the need to be culturally sensitive, consider food allergies, or to use other items more readily available within the house or classroom. Plastic snack bags, a heavy textbook, a permanent marker, and copies of the student worksheet. It might also be well to have a broom and a dustpan on hand for any potential cleanup. Start by using a permanent marker to label bags 1 through 4, as you can see labeled here. Bag 1 will represent healthy bone on Earth. To build this bone, you will use pieces of cereal to represent units of bone mass. As you add cereal to the bag, you need to keep count of how many pieces you add. You'll record the number of cereal pieces that you put into the bag on the data table from your worksheet. When counting the cereal pieces and deciding which ones to put in your bag, it's wise to choose cereal pieces that do not have existing imperfections. So if you happen to see cereal pieces that have holes or they're partial pieces, it's recommended that you not use these pieces. As best possible, try to find complete pieces of cereal to include in each bag. Fill bag 1 until there's very little room left, but make sure you can still close the bag completely and make sure that it's closed tightly. I also recommend placing bag number 1 with the pieces inside into a larger Ziploc baggie. Note how I have done that here and that the Ziploc bag is facing the opposite direction of the larger bag. This can help to contain any sort of mess that might happen should the cereal bag accidentally come open. Now that you know the number of pieces that we have in bag 1, which is our normal bone density here on Earth, you can then do the calculations for bone density of bag 2, bag 3, and bag 4. Let's say, for example, that you had 200 pieces of cereal in your first bag number 1. This is our original bone. It is considered 100%. Bag 2 is to be 80% of the original bone, so you would multiply 0.8 by the amount of cereal pieces in bag number 1, and for our example, that is 200 pieces. This means that bag number 2, representing 20% bone loss, would have 160 pieces of cereal. Again, we're using 200 as an example. You need to use whatever would fully fit and fill your bag 1. For bag 3, we want it to be 60% of the original bone. So you would multiply 0.6 by the amount of cereal pieces in bag number 1, which for our example was 200 pieces. So 0.6 times 200 means 120 pieces of cereal. This means bag 3, representing 40% bone loss, would have 120 pieces of cereal. For bag 4, we want that to represent 40% of the original bone, so you would multiply 0.4 by the amount of cereal pieces in bag number 1, which for our example was 200 pieces. This means bag number 4, representing 60% bone loss, would have 80 pieces of cereal. You now have your 4 bags of bones. Bag 1 represents 100% bone density on Earth. Bag 2 representing 80%. Bag 3, 60%, and bag 4 is 40%. Now it's time to see what happens when a bone is exposed to a sudden force, in our case, a book. Place bag 1 on a hard surface. Place a heavy book on top of that bag. Push down with a hard force. You're going to repeat this process for all bags 2 through 4 as well. You'll want to have the same person pushing down and to be mindful about the amount of force that they apply. Having the same person apply the force to all 4 bags provides more consistency in performing the demonstration. Now it's time to look at sample results and find out the number of remaining, we'll say, affected corn puffs. So empty out your bag and count the number of unaffected cereal pieces in each bag. Pieces that have dust on them from possibly other smashed pieces, or only a tiny flake taken off, should not be counted as affected. Be sure to record your data on the worksheet. So exactly how much bone was affected? Use this formula for each bag and record your values on your worksheet. To calculate the amount of bone that was damaged or affected, subtract the unaffected bone percentage from 100%. You can record this data on your worksheet. Once you've completed doing all of the data analysis, now it's important to analyze your results. Think about observations that you can make about the damage to the cereal pieces as the amount of cereal in the bags decreased. Imagine your bag was a real bone. What would happen if a sudden force was applied? How do you think we can prevent bone loss both on Earth and in space? Today's big idea in science was about bone density. We hope that you have enjoyed learning about how impact can affect bones of different densities and how disuse or inactivity can lead to a decrease in bone density.
Thanks for watching this NASA STEM EPDC Quick Bit. Don't forget to check out the description below for more information and links.